In this video, we're going to go over section 6.5 from our textbook, which is more on solving exponential and logarithmic equations. So remember from section 6.2, we saw several examples on how to solve what's called type 1 exponential equations. And so we did so by writing our equation as powers of the same base using this first property here. Now in this video, we're going to go over solving what's called type 2 exponential equations. And in this case, we can't easily write these equations as powers of the same base here. So our general strategy is to take the logarithm of both sides and apply the power rule to eliminate variable exponents. So in this video, we're just going to go over several examples of that, as well as use this second property here to solve log equations. So the first example here, we want to solve this exponential equation. 3 to the x is equal to 2. So, like we said, we can take the logarithm of both sides and apply the power rule to eliminate variable exponents. However, there are two different ways that we can solve this equation. So we'll do both of them now. We have 3x is equal to 2. What we could do is take log base 3 on both sides of this guy here. So we end up with log base 3 of 3x is equal to log base 3 of 2. Now we saw in the last video that these guys undo each other, and what happens is that this x drops back down, and we just end up with log base 3 of 2. Okay? So that's one way we can solve this, and this is actually called our exact form. So if you see that in the homework where it asks for the exact form, it would be in this form here. And then if it asks for a decimal, you can just plug this into your calculator and you'll find that this is roughly 0.6309. And then you'll just round it accordingly for the problem. The second way we can do this is what was mentioned above. We can take the natural log on both sides of this guy. What happens is we'll get ln of 3 to the x is equal to ln of 2. Using our power rule, this x is going to come down in front here. So we'll get x, whose ln of 3 is equal to ln of 2. Then solving for x by dividing by ln on both sides, we'll get ln of 2 divided by ln of 3. And so in this case, this would also be our exact form for our answer. And then plugging this into our calculator, we'll get the same thing here. Okay. So something to note here is that we could also just take log on both sides, so that would be log base 10, and we would do the same thing. Okay. So there are two different ways we can do this. Throughout the book, we primarily use this way, but I did just want to show you that we can use this property here and do it in only one step here, or one less step. All right, let's look at another example here. We want to solve this equation. So this guy's a little trickier. The best thing to do though is make sure that your term with your exponent is on one side by itself. So what we'll do is we'll subtract 2 on both sides of this guy. We'll get 5 e to the 3x is equal to 6. All right, next step is we'll divide by 5 on both sides. So we'll get e to the 3x is equal to 6 over 5. Now that we have our exponent by itself on one side, we can again take the natural log on both sides. So we'll get ln of e to the 3x is equal to ln of 6 over 5. Now in this case, remember ln and e are inverses of each other. So this guy cancels and our 3x comes down. And that's the same as if we were to use our power rule. We could do this here. Ln of e is just 1. So we get 3x is equal to ln of 6 over 5 here. Okay? So we could skip this step altogether and just recognize that these guys will undo each other, so this exponent comes down, but this is the reason why that's happening, because of the power rule. All right, now solving for x here, we'll get x is equal to ln of 6 over 5 divided by 3. So this would be our answer, our exact answer for this problem. All right, let's look at another example. We want to solve this guy here. The first thing we'll do is take the natural log on both sides. So we'll get ln of 4 to the x minus 2 is equal to ln of 3 to the 2x. All right. Now using our power rule here, we're going to bring this exponent down in front. So we have x minus 2 times ln of 4. And similarly on this side, we'll bring this power down in front. So we'll get 2x times ln of 3. All right. Now what we'll do is we'll distribute this ln of 4 to both terms in this binomial here. So we'll get x ln 4 minus 2 ln of 4. And on this side, we still have our 2x ln of 3 here. All right, so now what I'm going to want to do is get all of my terms with an x in them on one side. So we'll move this 2x times ln 3 on this side, and then we'll move this minus 2 ln 4 on this side. Doing so, we'll get x ln of 4 minus 2x ln of 3. Like we said, just moving this guy over, so we'll have to subtract on both sides. And then on our right-hand side, we'll get positive 2 ln 4. Again, we want to move this guy over, so we'll add 2 ln 4 to both sides. Now that I have both terms with an x in them on this side, I can factor out an x out. So we'll get ln 4 minus 2 ln 3 times x. And we still have our 2 ln 4 on the right-hand side. Now solving for x, what we'll do is we'll just divide by this term here. So we'll get 2 ln of 4 divided by ln of 4 minus 2 ln of 3. All right, so this will be our final answer. And we can rewrite this with our power rule. So we could write this as ln 4 squared, and then ln of 3 squared here, and then also use our quotient rule here to write this as a quotient and then simplify it. But for the MyLab math homework, it does want it in this expanded form. So we'll stop there. Let's look at this next example here. We want to solve this equation. So in this case, what we're going to do is use property B above. So like I said, we'll be using that to solve our log equations here. So if we have that x and y are some numbers that are greater than 0, then log base b of x is going to be equal to log base b of y if and only if x and y are equal. So we'll use this property to solve the next couple examples. First, what we'll do is we'll rewrite everything on each side of our equal sign as just one log with coefficient 1. So in this case, we'll use our quotient rule. So this will be ln of 4x plus 3 divided by x is equal to ln of 5. Okay? So we just rewrote this using our quotient rule. Now, from property b above, remember we said log base b of something is equal to log base b of something else. So if these guys are the same, this is the case if and only if the arguments for our log functions are equal to each other. So this means that 4x plus 3 over x must be equal to 5. Right? So this guy becomes a little simpler. Multiplying by x on both sides, we get this here. And then what we can do is subtract 4 on both sides here. This tells us that x is going to be equal to 3. All right. For the next example, we'll also use this property, but again, first thing you're going to want to do is write this as a single log. So on the left-hand side, we'll have log base 3 of 7x over x plus 4 is equal to log base 3 of x on this side. And again, if these log functions here are the same, then that means these guys must be equal to each other. The arguments must be equal. So we'll have 7x over x plus 4 is going to be equal to x. We'll do the same thing here. We'll multiply by x plus 4 on both sides. So here we'll get 7x is equal to x squared plus 4x. Then what we'll do is we'll subtract 7x on both sides of this guy. So we get x squared minus 3x is equal to 0. So just moving this 7x here, so subtracting 7x on both sides. Factoring this, we'll get x times x minus 3 is equal to 0. So this tells us that x is equal to 0 and x is equal to positive 3. However, remember the domain for our log functions is all numbers x that are greater than 0. So our domain is 0 to infinity, so this means this x is equal to 0 here is not in our solution set. So our only answer here is x is equal to 3.